I made a CPU using a $20 FPGA. There's nothing too fancy about it, but I can transfer the CPU instructions into it, and it will print out the hello world, which is pretty cool. For the rest of the video, I'll be explaining the design of the CPU. The design is actually based on the AZ Processor SoC design from the book CPU 自制入门. If you don't understand Chinese, let me translate that for you. It means go make CPU yourself lah, aiyo. The book was originally written by the Japanese author 水头一寿、米泽辽、藤田义士, and it was later translated into Chinese by Zhao Qian. And now I've ported it to the cheapest FPGA in the world. And my name is... It's your boy Chen Ende. This is the system overview of the AZ Processor SoC. If you do not know what is SoC, please take note that SoC has nothing to do with SOB. SoC means System on Chip. As you can see here, our SoC consists of a CPU along with its peripherals such as ROM, RAM, timer, UART, and also GPIO. This is the overview of the video. So in part 1, we'll see the RTL design, which includes the CPU design such as the pipeline, hazard mitigation, interrupt, and exception handling. We'll see how to generate a RAM, ROM, and PLL in quarters so that we don't have to code it in Verilog. And then the I/O design, which includes the GPIO, timer, and UART. And we will also see the bus protocol to connect all this I/O to the CPU. And finally, we'll see the RTL simulation in ModelSim that prints hello world. In part 2, we'll be focusing on the hardware design. We'll see the pin assignment for the FPGA and its connection with the hardware circuit. I'll also show the debugging tips using the SignalTap Logic Analyzer. In the part 3, we'll see the software design. So we'll see the XMODEM protocol to transfer the binaries to the FPGA via the UART. And then we'll see some demo such as the kitchen timer demo. So let's go to the part 1, which is the RTL design. This CPU design is based on the classic 5-stage pipeline. And as you can see here, this whole thing is the CPU. And it is connected to this I/O via the bus. So now the question is, why is it called 5-stage pipeline? Well, how do you eat an elephant? You break it down into pieces, right? So in the same way, the CPU breaks down the whole computation thing into 5 stages. In the first stage, we have the instruction fetch stage. In this stage, we have a program counter to keep track of where are we currently executing. Using this counter, we can get the instruction from either the RAM or the ROM. And then we can pass the instruction into the next stage, which is instruction decode stage. In this stage, we have a decoder to decode the instruction into the opcode and also the operands. And the operands can come from the general purpose register or control register or immediate values. With this opcode and operands, we can now go to the execution stage where we will do the computation based on them. So we have a ALU to compute and then pass the result into the next stage, which is the memory stage. In the memory stage, depending on the instruction, we may need to write the result back into the memory, or maybe we need to read the data from memory, or maybe we don't even need to access the memory at all. It all depends on the instruction. And using the result from the ALU or the data loaded from the memory, we can then pass them, we can pass it to the write back stage where it can be written back into the general purpose register or the control register. Again, this write back depends on the instruction. It doesn't have to happen it doesn't have to happen for every instruction. And here we have a controller. This is like a supervisor. It checks the interrupt exception and then determine whether it needs to store or flush all the register or not. And if you notice here, we have this forwarding, and I will explain this in the next slide. Now let's talk about the CPU hazards. Structural hazard is one of them. In our processor design, we have the instruction fetch stage and memory stage sharing a same dual port RAM. And this may be problematic when accessing the same RAM address by the two stages. Concurrent read to the same RAM address is not a problem. But if concurrent write to the same RAM address, there will be problem. Luckily, in our design, this concurrent write problem doesn't occur because the instruction fetch stage never write into the RAM. It only reads. And concurrent read and write from and to the RAM is possible in our design, but for simplicity, we don't handle them, so the self-modifying code may not work properly. And in our assembly program, we actually never do this, which is very rare to modify the code while we are executing them at the same time. The second type of CPU hazard that we are looking at is the data hazard. This hazard may happen when an instruction may depend on the result of the previous instruction, which has not been written yet. So now let's look at an example. The first possible data hazard scenario in our processor design is that the instruction decoding stage needs the GPR data that has not been written yet by the execution or memory stage. This is also known as the read after write hazard, because in the instruction decoding stage, we are trying to read, while before that, the write has not been completed yet. To visualize this scenario, let's look at the CPU pipeline diagram. So let's say we have 3 instructions to be executed consecutively. So this, for the first instruction, at this point in time, it is being fetched. And in this point of time, the second instruction is being fetched, while this first instruction is in the decoding stage. And in this point of time, there is some problem, because our second instruction needs this GPR3 from the first instruction, while our first instruction is still in the execution stage, which means this GPR3 has not been written back into the actual GPR yet. So this is how a data hazard can occur. And because we need this GPR3 in the second instruction, which is currently in the instruction decode stage, what we can do is forward this GPR3 from the execution stage directly into the ID stage. So we don't have to store the CPU pipeline and wait for the GPR3 to be written back in the write back stage, and then only then we do the ID stage. We don't have to do that. All we need is to forward the needed data from the execution stage directly into the instruction decode stage. And similarly, for this third instruction, at this point in time, this third instruction is one is needing this GPR3 and GPR5 from the previous two instructions. And again, these two instructions are still in the memory stage and execution stage. They haven't reached the write back stage where they can write back to the GPR. So the actual GPR still holds the old value. And in this case, we can do the same thing, which is forward the needed data from the execution stage and also the memory stage. So hopefully it's now clear why we have these two arrows here for the forwarding purpose. This is how the forwarding looks like in the RTL coding. So we are checking the execution stage to see whether by the way, this ID underscore DST address is the instruction decode destination address. Technically, this address is actually in the execution stage despite of the prefix of ID, because we are giving the execution stage this destination address. So we are checking this in the execution stage to see whether in the execution stage we have a instruction that is trying to write into the GPR address having the same address with the GPR address that we are trying to decode. If so, we will get the forwarded data from the execution stage into our decoder. And we also need to check from the mem stage as well. Again, despite of this EX prefix, this thing is actually in the mem stage because we are giving the mem stage this address that we passed from the EX stage. So technically this is in the mem stage. So we are checking whether we have an instruction in the mem stage that is trying to write into the same address that we are trying to decode. If so, then we forward the mem stage data into the decode stage. Else, we just read it from the GPR like usual. By the way, this RA register is the operands that the decoder is giving to this, and this is operand 2. RA is the operand 1, and the same logic apply for the operand 2. Also, I want to point out the reason why we are giving the precedence to the forwarded data from the execution stage over the forwarded data from the mem stage. This is because in the EX stage, it is holding the latest instruction that is previous to our currently decoding instruction. So whatever, let's say in the mem stage, we are writing to the RA address. And then in the EX stage, we are also writing to the RA address. And because this EX, the instruction in the EX stage is more recent than the instruction in the mem stage, So the data at the RA address will be overwritten by the EX stage. So that's why we give the precedence to the forwarded data from execution stage. The second possible data hazard scenario is when the ID stage needs memory data that has not been loaded yet, because the memory loading has to happen in the mem stage. And this is also known as the load hazard. In this example, we are trying to execute this instruction and also this instruction. Let's ignore the bottom line first. So in the second instruction, let's say when it is in the instruction decode stage, it is requiring the GPR3. And this GPR3 comes from the first instruction. Where does this GPR3 comes from? It comes from the memory. But if we look at here, this first instruction is still in the execution stage. It is impossible that we forward the memory data from the point in the future back into the current time. So this requires us to store for one cycle for this second instruction. So after we store for one cycle, it will look like this. And we have this scenario where the second instruction is now in the decoding stage, and it can get the forwarded data from the memory stage and continues the execution normally. This is how the load hazard in the scenario 2 is detected. Here we are checking in the execution stage whether we are having a memory load operation that is trying to load into this GPR address. And if this GPR address that we are going to load memory into is the same with the GPR address that we are trying to decode, then we have detected the load hazard. Therefore, we set it to enable. Just now I mentioned about the pipeline store. So now it's time to talk more about it. A pipeline store is nothing but maintaining the pipeline registers with its previous value. Means it's not changing in the next clock cycle. And obviously, one of the scenario where we need to store is when both the instruction fetch stage and the memory stage is busy accessing the bus. This causes the pipeline to not be able to continue. That's why stalling is needed. As you can see here, this is the stall signal when the IF stage or the memory stage is busy. And as discussed just now, when we have the load hazard, we will need to store the instruction fetch stage. So we store that using the IF store signal. We don't have to store the other stages because the load hazard only needs to store the ID stage, which is requiring the memory load data. And as a side note, the load hazard will also flush out the ID stage because the ID stage is being stored and there is no point in continuing the instruction that has been decoded in the ID stage. There are also other data hazards, but in our processor, the write after write hazard never happens because write operation always happen sequentially. As for the write after read hazard, it never happens in our processor because read is always happening before the write operation. Let's move on to the third type of the CPU hazard, which is the control hazard. This hazard affects instructions that cause program counter branching or jumping. For example, the instruction branch, call, jump, or return from a session. All of these instructions will cause the jumping of the program counter. And in our processor, we don't use any fancy branch prediction algorithm. We simply put a branch delay slot. So let's see what is a branch delay slot. So here is the branching instruction, which may or may not cause the jumping of the program counter. When this first instruction is in the decoding stage, it is actually useless to fetch at this point. Because at this point, at this orange line here, actually the address register has already been updated with the next instruction after this branching instruction. And even though we can technically determine the branching address in the decoding stage, we are already too late to update the address register feeding into the synchronous RAM or ROM. As a result, since we are not using any branch prediction, we might as well just fetch a NOP instruction here. So now the question is, who will insert this NOP instruction after the branching instruction? Well, for simplicity, our processor mandates that the software developer slot in a dummy NOP assembly instruction after each of these branching instructions. Moving on to the next topic, we have interrupt and also the exception. What are the differences between two of them? Well, in the interrupt, it is hardware induced, meaning it is due to the external interrupt due to the external devices. For exception, it is software induced, which means that it can be caused by for example, the computation has overflowed, or there is trap instruction, undefined instruction, or misaligned memory access. For simplicity, in our processor, we do not have an interrupt vector table. What we do is that we share a single handler between the interrupt and exception. First, let's talk about the interrupt. Interrupt is checked in the execution stage. When the interrupt is detected, then the main thing that we'll do in the execution stage is to set the exception code to interrupt. This way, when we pass up this exception code up to the write back stage, the controller will be able to know that interrupt has happened to the instruction at the address at pre-program counter, and also the branch flag will tell whether the interrupted instruction is the branch delay slot. The reason we don't take the main PC as the program counter when the instruction is interrupted is because in our design, the main PC is always pointing to the next instruction. What we are interested is the current instruction. Therefore, we introduce a flip-flop to store the program counter before this. The almost same explanation can be said for the branch flag. We don't take the main branch flag directly because the branch flag is telling whether the current instruction is a branching instruction or not. However, what we are interested in is whether the current instruction is the branch delay slot after the branching instruction. Therefore, we again introduce a flip-flop to store this branch flag. Unlike the interrupt, exception will be checked in many stages. For example, in the decoder stage, we can check the exception due to the trap instruction or undefined instruction, or when we are accessing the control register while we are in the user mode, which is a form of privilege violation. And in the execution stage, we can check for the ALU overflow exception, while in the memory stage, we can check for the memory. We can check for the misaligned access to the memory. Similar to the interrupt, the exception code is set accordingly and will be passed up to the write back stage for the controller to handle. When we are in the write back stage, the controller will check the exception code. If the exception code has something wrong with it, then the controller needs to flush out the pipeline registers. What flushing does is it reinitializes the pipeline registers. Basically, flushing is needed whenever the CPU is in a totally new state. In the case of encountering an exception, we need to flush out the pipeline because all of the later instructions are now useless, while our current instruction has already encountered exception. Also, when we return from the exception, we also need to flush out the pipeline to reflect the fact that we are switching the execution mode from kernel mode to the user mode. And third scenario is when we write to the control register. Again, this is needed because all of the later instructions in the pipeline may have already started and was using all control register value. These three scenarios have been shown here in the RTL code. So in the write back stage, this is to check whether we have encountered any abnormal exception. And if not, then we check whether we have a return from exception instruction, or we have the write to control register instruction. If any of this is true, then we need to flush. This flush signal will affect all of the pipeline register. When there is interrupt or exception, the hardware automatically sets the program counter and also the branching flag, so that later on the software interrupt handler can check the delay flag in control register C5 to see whether the instruction being interrupted was a branch delay slot or not. And it will also set the execution mode to be restored by the EXRT instruction, and then it will switch to the kernel mode to handle this interrupt or exception. The interrupt enable flag is also set so that it can be restored during the EXRT instruction. And while handling the interrupt or exception handler, the hardware automatically disables the interrupt, and therefore we simplify the design such that we don't have to consider nested interrupt. So this is the RTL code for the EXRT. When we return from the exception, the execution mode and also the interrupt enable will be restored. Here's a typical interrupt handler. Near the end of it, the hardware requires software developer to check for the control register C5, which contains the delay flag, to see whether the instruction being interrupted was a branch delay slot or not. In case it's not a branch delay slot, then we are good to go to the return from exception instruction. However, if it was a branch delay slot, then we need to additionally load the control register C3, which contains the instruction address that was interrupted, and we need to subtract 4 from it. By the way, we subtract 4 because one instruction takes 4 bytes in our design, and by subtracting 4, we are essentially getting the branching instruction just above the branch delay slot. And then we return to the branching instruction that we have calculated here. The reason we are returning to the branching instruction is because in our hardware, we don't save any branching address that we determine from the branching instruction. As a result, if we simply return back to the branch delay slot, we are actually losing the branching address, which is not a good thing. Alright, enough of the theory on the CPU design. Now let's move on to the peripherals. The first peripheral that I'm going to talk about is the memory. There are two types of memory on our SoC. The first type is the RAM, which is made of the dual port RAM. We need dual port because both the instruction fetching stage and the memory stage will use it. So for the ROM, we only need the single port ROM because we only have instruction fetching stage that will read from it. And since this is a simplified project that focuses on the CPU design, we won't include the MMU and cache design into our SoC. For the RAM and the ROM, we actually don't have to write any Verilog code. We can just use the IP provided by Quartus. To generate the RAM, we can go to the Mega Wizard plugin manager in Quartus and choose the RAM 2 port, and window like this will pop up. And due to the limited amount of RAM in my chip FPGA, I have intentionally shrink it down to 1K for the memory depth. And I've included the slide in the GitHub repo. Feel free to look at it and copy the setting, but most of the setting I have already left it as default. And when you generate the Mega Wizard function, and actually these checkboxes are not needed. I check those just for example purpose. As for the ROM, we need to embed the binary into it using the memory initialization file format MIF. This is the memory initialization file format for the Quartus. So from here, we have written an assembly program in the .asm file format. We can pass it to the provider assembler to produce the binary file. And I've written tools in Python to convert the binary into the MIF file usable by the Quartus. And using this MIF, we can embed it in the Mega Wizard ROM. Let's see how to do it. As a reminder, the tools mentioned just now can be found on my GitHub page. This is the assembler. This is the binary to MIF converter that I've written. And this is the build script that will invoke this assembler to compile all of the demo program in these folders. So when you run the build.bat, then you will see the compilation starts and then where are the MIF file being written to. And again, due to the limited size of my chip FPGA, I have intentionally shrink down the memory depth to 1K. Here's where you can browse and choose the MIF file to be embedded in the ROM. Here I'm using the loader file because this loader file is able to receive the binary from the laptop via XMODEM protocol using the UART design on the SoC. And this will greatly improve the speed of software development because whenever I have a new program, I don't have to come over here and include it and then recompile and reprogram the FPGA. That's a lot of work. Well, I can just use this loader to get the program from my laptop directly via the XMODEM protocol. Next, let's see how to generate the clock and reset in the Mega Wizard function. The Altera equivalent of Xilinx DCM is basically this PLL. The PLL has a locked signal to tell if the generated clock is ready to be used or not. And we can use this locked signal as a signal to reset the flip-flops in our design. And this PLL is resettable via the external reset software input. This is the hardware switch connected externally to our SoC. So this is the Mega Wizard plugin for the Altera PLL. In my FPGA, the onboard reference clock is 50 MHz, and here we scale it down by a factor of 5 so that we get 10 MHz into our FPGA design. For the other settings, I've left it to the default, and for the second clock, the C1 clock, I've set the phase to 180 to invert it. This is a trick to read from the RAM in the same clock cycle. This gives the illusion that we have an asynchronous RAM, while actually what we do is that we use the next half cycle to get the data from the RAM. This is a trick to give an illusion that we are using an asynchronous RAM, while actually what we are doing is that we are reading out the data using the inverted clock in the half cycle. And this gives an illusion that we can read out the RAM data in the same clock cycle. Now let's look at the GPIO. It has three types, which are input, output, and bidirectional. This bidirectional means that it can be configured as input or output. And this GPIO, just like any other peripheral, it is an MMIO device. So for example, we can read from this memory location to see the input data, or we can write into this output address location so that we can set the output pin. And for bidirectional pin, we can set the direction using this directional setting register. Next, we have the timer. The timer is a up counter. It generates interrupt once the counter value reaches a programmable threshold value. So this is the threshold value. And we can have periodic mode or one-shot mode, which is settable in this control register. And this interrupt register is fit into the CPU so that the CPU controller can check whether interrupt has occurred, and this is the counter value. And we can write into this counter value to update the next time when the interrupt should occur. For the UART, there is no parity checking, and for simplicity, there is no hardware transmitter or receiver buffer provided. This means that data needs to be transmitted or received by the software 1 byte by 1 byte. This shouldn't be a problem because the UART baud rate is quite slow, which is 38,400, while the CPU is running at a high speed of 10 MHz. And for the register, we have control register, and these 2 bits are for telling whether the transmitter or the receiver is busy doing their work. Once they are done doing their work, they can raise this interrupt bits to indicate that they are done. And for the data to transmit or the data to be the data received, we can obtain from this data register here. The last component in our SoC is the bus. The bus functions to connect the peripherals with the CPU. A bus can have multiple slaves. Basically, each peripheral is a slave and is accessed as an MMIO device via the bus. The bus address decoder helps to determine which peripheral to access. And for simplicity, we only have 8 slaves can be used in our design, and we may increase the number of slaves at the expense of less usable memory range for each peripheral. So for the 8 slaves, we are not using all of them. As you can see, the last 3 are unused. And we connect the ROM, RAM, timer, and UART and the GPIO to it. For the slave index, we are taking the 3 most significant bits from the 32-bit address. The bus can have multiple masters as well. In our design, the 2 masters are the instruction fetching stage and also the memory stage. These 2 stages may compete with each other for the bus access. And the solution for this competition is to use a bus arbiter. This bus arbiter uses the round-robin algorithm to determine which of the master should take turn to get the access to the bus. And also, the master that is holding the bus must voluntarily release it for the other master to use. This is the bus access lifecycle. Firstly, the master requests the bus access, and the round-robin bus arbiter will grant the master the bus access. The master will then provide the address that it wants to access. Then the bus decoder chip select signal will be set to the proper slave chip select, and then the master will set the operation to either read or write along with the data to write in case of the write operation. Master will then use a address select pulse to tell the slave that it should start processing the data. When the slave notices that, it will process the operation accordingly. And this is how it looks like in the RTL coding. So the slave will check whether it is currently selected with the chip select and whether the address provided by the master is a valid one. And also it will check to see whether it is getting the read operation or the write operation. And then it will process the operation accordingly in the switch case statement here. When the operation is done, the slave will give the ready signal to tell the master that it has done the operation. Master now knows that the operation is done and take in the reading in case of read operation. And next, the master releases the bus access request so that the bus arbiter is now free to grant access to the other master. Now that we have done discussing all of the components of the SoC, it's time to move on to the quarters. So when you want to compile the project, you will notice that I've already included all of the header files in this project libraries in the quarters setting. And to do the ModelSim simulation, firstly, create a new ModelSim project in the folder named 3sim and then add all the Verilog files, including the Verilog files generated from the Mega Wizard. In my repo, I've put the Verilog coding and also the test bench in these two folders. And take note that we do not need to include the header files. Inside the 3sim folder, I provided a sample.do script to run the simulation for serial program that will print hello world. Before running the script, also make sure to have the serial.bin.mif embedded in the ROM and then recompile the design. Then when you go to the ModelSim and you do the chip-top-test.do script and waiting for a while, then you will see the waveform being generated. And also, most importantly, you will see the hello world being printed out here. Now let's take a closer look at the provided.do script. You will see that to simulate the Mega Wizard component in ModelSim, I'm using this command. Basically, this command is to start the vsim with the option to stop when the simulation encounter this finish command in the test bench. And because we are simulating Mega Wizard component, we need to include the Altera Mega Wizard function library. And this underscore ver means that it is an Verilog library. We need to include this because we are using the Altera generated PLL, RAM, and ROM. And for this WLF, it is for the saving of the output of the waveform so that we can view it later without any resimulation. And this optional arguments is to increase the visibility during the debugging. And lastly, we specify the name of our test bench, which is chip-top test in this case. There are two methods to save the simulation waveform for view later on without resimulation. For the first method, we can use the wavelog format when we invoke the ModelSim vsim. And here is the example that I've shown just now. When you run this line of command manually in the ModelSim, then you will go into the simulation mode. And in the wave window, you can drag and drop instances to be inspected. And then in the transcript window, you will see the corresponding commands to the adding waveform action that you have just performed just now. You may copy paste them into the test.do file, or you can simply save the commands as a separate .do file. You can go to here, file, save format, and then save it into, for example, chip top test waveform.do file. And then in your main.do file, you can then source this waveform file to set up the wave window. With this wave log format specified, when you run all, it will log into the wave log format for view later on. So here's what I mean by sourcing the waveform.do file. This is the main.do file. Inside it, we can source the saved waveform.do file. As you can see, the waveform.do file inside it, what it does is adding the wave corresponding to the signals into the waveform window. So we can do that by sourcing this .do file to set up our wave window, and then we will run all to save the wave log into the wave log format. The second method is to use the dump vars in the test bench. This is more portable, such as we can view it in the GTK wave. So inside our test bench, we need to specify where to dump the VCD. And we can specify the signals to be captured. We can capture the signals by module, like this. And this is the ROM module. We are dumping the vars from the chip.rom modules. Or we can capture a single signal, such as this. We are capturing the clock generated log signal from the Altera PLL. And in ModelSim, we need to convert the VCD into wavelog format so that the ModelSim can view it. To view the wavelog format file, we can use this command and specify the wavelog format that we want to view. At this point, there will be nothing in the wave window, and we need to manually drag and drop which instance to inspect in the wave window. And to quit, we can use this command dataset close, which is this name right here, the same name with the wavelog format. And it seems like it is not possible to save the output from the display, monitor, write, strobe, etc. in the wavelog format or VCD, because this wavelog format or VCD are saving only the output of the wave window. So I don't think there's a way to save the transcript window output. Moving on to part 2 about the hardware design. And first, I'll talk about the FPGA pin assignment along with the circuit connection. Here is the overview of the connection. For the pin 17 of the FPGA, I've connected it to the onboard 50 MHz reference clock. And for the GPIO in, I've connected them to the active high push button. As for the GPIO bidirectional pins, I left them floating, and I've modified the RTL so that the direction of these bidirectional pins is set to the output direction by default, so that it's okay to left them floating. And this will simplify the circuit connection because I don't have to connect any wires for all these pins. And for GPIO out, I've connected them with red, blue, green LEDs and also two 7-segment displays. And the 7-segment displays are common cathode type. For the reset switch, I've connected it to the active low power on circuit with a push button. And lastly, for the UART, RX and TX, I've connected them to the TX and RX of the UART module. This is how the actual hardware looks like. We have the USB blaster to download the program into the FPGA. And we also have this UART module so that we can communicate with our laptop via the UART with our FPGA. And this is the input board for the GPIO in and reset switch. And we also have output board connected to GPIO out, which will write out the 7-segment displays, 3 LEDs, and also the buzzer. Now let's look at the input board first. For the input board, this is my switch 1, switch 2, switch 3, and also switch 4. And this is my power on reset button. And all of these are connected to the FPGA via the straight pin header here. This is the schematic for the input board. So this is the straight pin header. And we have VCC from the FPGA to power up this input board. When this board is powered up, we can have a red LED to indicate the power status. And we also need the ground from the FPGA. And then this is connected to the reset switch, which is actually an active low power on reset circuit with a user resetable push button here. And for switch 1 to switch 4, it is actually a tab. And for switch 1 to switch 4, we are having the active high input. And when we push this push button, then this switch will be high. So that's why it's called active high. And also I've added LED so that when we push the push button, the LED will light up. Now let's take a closer look at the output board. For the output board, we have 3 LEDs, 1 buzzer, and also the common cathode 7-segment displays. The schematic is quite straightforward. This is the ground from the FPGA, and all of these pins are from the GPIO out of the FPGA connected to the 7-segment displays. And we also have 3 LED for indication purpose, and also 1 buzzer for the alarm purpose. For the FT232 module, we connect the UART RX of the FPGA to the TX of the module, and TX of the FPGA to the RX of the module. And make sure to connect the 3.3 volt jumper because we are using 3.3 volt logic here. And we don't have to connect the VCC. We only need to connect the ground because we have already powered up the module using the USB port. Next, we'll see how to use the SignalTap Logic Analyzer as a real-time debugger to see what is inside the FPGA design. So the SignalTap Logic Analyzer is located under the Tools tab of the quarters. In the SignalTap Logic Analyzer, we need to specify the reference clock in the signal configuration. And when we press this button, it will go to the node finder and we can select the pre-synthesis and then search using the wildcard CLK. And then we'll get the clock signal. And then we press this button to select the node and then click OK. And then click OK. Then it will appear here. For the sample depth, I'm using 64 only because I'm using a cheap FPGA without much RAM, so I need to use low sample depth value. Else error like this will occur. It complains that the selected device has no sufficient RAM location. And for the triggering, you can try to play around with the trigger position, but usually I just set it to the pre-trigger. Next, we will need to add in the signal that we want to inspect. So when we right click in the trigger window here, we go to the add nodes and the node finder window will pop up. And then we again can use the wildcard to search for the signal that we want. In this case, we are trying to see the GPIO in. And then click this button to select the node and then click OK. Then it will appear in the trigger window. At this point, you will see the red message like this telling you to compile the project to continue. Before we compile a project, we can also change the capture edge of the signal. For example, in this case, I'm interested in the rising edge of the GPIO in. And because we are interested in either of the rising edge of any of this GPIO in, we should set the all condition in the trigger condition. After setting up the trigger condition, we need to go back to the quarters to recompile the design. And after compilation, we'll see in the SignalTap Analyzer that we need to program the device to continue. At this point, if the hardware is not listed yet in this row, then we need to set up and also we can try to scan chain so that it will appear here. Then we are ready to download the design by pressing this button. After we download the design, then we can run the analysis, run the debugger. This button is for capturing once, while this button is for capturing continuously. Here's the SignalTap demo. First, we go and download the design, and then we run the debugger continuously. At this point, when I press the push button, this is switch 1. Switch 1 is connected to the GPIO in index 0 of our FPGA. So let's press it. And now the capture data can be seen here. So as you can see, the rising edge has been captured successfully. If I press the switch 2, which is connected to a GPIO in 1, then you can see that it has been captured as well. This is switch 3. This is switch 4. And by the way, the reason we are seeing more than one rising edges from the GPIO in is because this hardware design doesn't have a proper debugging using the Smith trigger input. When I purchased this FPGA, I was expecting it to have Smith trigger input configurable at their pins, but turns out that there is none. And I've already designed the circuit without the debugging mechanism. So I have to deal with it because I don't want to modify my hardware input here. I'm running out of time for the next project actually. So I have to use software debugging. In order to disable SignalTap in our final design, we can go to Assignments, Settings, and under here we can untick this Enable SignalTap Logic Analyzer checkbox. And then we recompile the design without this SignalTap included. Now let's discuss the part 3, the final part, which is the software design. Inside the FPGA, there is a program embedded in the ROM, and the program is a loader. Loader is a program such that when we press any of the switch 1 to switch 4, the program will start to get the binary data from the laptop term using the XMODEM protocol. The data obtained will be stored into the RAM, and once we are done obtaining all the binary data, then the program will jump and execute at the RAM address. Now, if we have another binary to test out, we just press the reset switch button and then repeat all of the steps above. This helps to speed up the software development greatly because we don't have to recompile the FPGA design whenever we want to run and test another binary file. Here is the XMODEM packet format. Take note that there are many bytes in a packet, but each of the byte is transmitted as one UART transaction. So the packet format consists of the SOS, which is the start of heading. In hex, this is 1, and then for the BN, it is block number, while BNC is the binary complement of BN, such that when we add this together, we can check that whether we are getting the FF. And here we have the checksum. Checksum is the sum of the bytes in the packet modulo 256. This is for packet error checking as well. As for the data, these are the actual things that we write into the RAM before jumping the program counter to start executing at the RAM. To transfer binary data from the laptop to our FPGA. So at the laptop, we start the XMODEM server here, and we wait for the next signal from the CPU, our FPGA. So in our loader program, when we press any of the switch 1 to switch 4, the FPGA will send the next signal, and then the laptop will start to send the first packet to the receiver. Upon receiving the first packet, the receiver will reply with the acknowledge. And then this continues. And let's say in between, we have one of the packet with checksum error. In this case, the receiver should send the next. And the sender will then resend the packet. And the process continues until the sender tells the receiver that we are at the end of transmission, which means there are no more data to be transferred. And then finally, the receiver will acknowledge. In our loader program, for each of the packet, we will extract the data bytes from the packet and then write it into the RAM region. And when the transmission has ended, our loader program will jump to the RAM region and start executing there. Let's see the transferring of the binary data from our laptop into the FPGA in action. So the first thing that we do is we reset the board first so that it starts executing from the ROM, which is the location of the loader program. and then we go to the transfer XMODEM, send, and I'm going to demo the kitchen timer program. Double click. At this point, the Teraterm server is trying to get the next signal from the FPGA. So in the loader program, whenever we press any one of the switch, then the transmission will start. So let's press any one of this. So now the program has already completed transferring into the FPGA, and you can see that we have already jumped to the RAM address and start executing the binary. Now this is the real-time testing of the kitchen timer. On the left we have a timer from the Windows program, and on the right we have the timer program that we have written. So let's compare the two of them. And to set the time to 1 minute and 23 seconds, the first thing that we do is we set the minute first. So this button is the plus button, and this is the minus button, and this is the switch to switch between the minute setting and also the second setting. So right now, as you can see, we have the red LED, which indicates that we are setting for the minute, and for the minute we want to have 1 minute. So this is 1 minute, and for the second I want to have 23. So let's add this until it is 23. Alright, now we are ready to start the test. I need to press this start button and the start button on my Windows using the mouse. So let's do it. 1, 2, 3. As we are counting down, we can see the green LED flashing. See, it works. Now the buzzer is making the noise while the LED is flashing like a police car. If you are a drug dealer, you must have seen this multiple times before. Okay. To reset the timer, we just press this button.